Hello Math 1093, this is Dr. P with A Hidden Gem. In this video I'm going to solve a problem about triangle geometry. In this problem we are given a triangle and we follow the usual conventions. The triangle has vertices which I call A, B, and C capital letters. I should probably make that one a little more pronounced there. Let's make that a big capital C. There we go. We are given a triangle ABC, and that triangle has of course three sides which have length lowercase a, lowercase b, and over here lowercase c, even though I haven't written it yet. And you'll notice lowercase a is opposite vertex A, lowercase b is opposite vertex b, and so on. And we also have three interior angles. I've only marked one of them, and we call that one capital C. Sometimes I'll use capital C to mean a vertex. Sometimes I use it to mean an angle measure. Just try to keep up. All right, so now the question is, if I'm given these three values, the length of A, the length B, and the angle measure C, can I figure out the length of this other side? All right, and the tricky part is I'm not going to actually say what the values of A and B and the angle measure C are. We are just going to assume that they're given and see if we can find this other side length in terms of those. Okay, and to do that we're going to use a little bit of coordinate geometry. In other words, I'm going to take this triangle and embed it in a coordinate plane, because we're very used to working with trigonometric functions in the context of a circle in the coordinate plane, so I kind of want to take advantage of that here. So I'm going to draw a set of coordinate axes and then try to work out what the coordinates of all these points are. So first of all, I think that if this is the origin, then I can find the coordinates of this point here. The coordinates of that point will just be, well, something comma 0, because I'm definitely on the x-axis here. But what's the x-coordinate? Well, the x-coordinate, because I am traveling a units out from the origin, the x-coordinate is just a. So that is the point a comma 0. All right. Now, what about this other point here? See, the thinking that I'm using here is if I could find the coordinates of both of these points, this point and this point, then I would be able to use the distance formula from geometry to find the length of this side. That's what I'm hoping for anyway. So what are the coordinates of this other point, point A? The coordinates of that point are going to be, well, I guess I haven't thought about this very much. So what I might do, I know that this is at the end of a line segment that emanates from the origin, and I know what the angle of that segment is from the positive horizontal axis. So I'm going to use trigonometry to do this. I'm going to draw a circle that goes through that point. So I'm going to draw a circle like this. Let's see. Try and go through this point. There we go. Going to look kind of weird, I guess. Just my circle drawing skills are a little bit off today. All right, and this is going to go through the circle, which is perfectly okay. It's not necessarily going to go through that other vertex because A and B might be different. But anyway, well, that's a decent circle anyway. So what are the coordinates of this point? Well, you may remember that we know that the cosine of C is equal to x over r, and the sine of C is equal to y over r, where x and y are the coordinates of that point. Okay, the radius in this case is b, because I know that the length of this line segment here is b. So now the question is just how do I write x and y in terms of known quantities? Well, x is going to be equal to, if I multiply this equation both sides by r, I get x equals r times cosine of c. So since the radius is b, that is b times cosine of c. And y is going to be r times sine of c. So that's going to be b times sine of c. So the coordinates of this point here, point A, the coordinates of that point are b cosine of c, comma, b sine of c. So now what I'm going to do is I'm going to use the distance formula to get the length c. All right, the distance formula tells me that c is the square root of, actually I wrote a huge square root for some reason, but really all I wanted to say is that this is going to be the square root of x2 minus x1 squared plus y2 minus y1 squared. I guess that just gave myself more room to write that formula. In other words, the distance formula just tells us that the length of C, that is the length of this segment here, I'm going to go ahead and put a C there just so we know what we were talking about. That's C, lowercase c. So the length of that line segment is the square root of the difference between the x coordinates of these 2 points, this one A and this one B, and the square of the difference between the y coordinates of this point and this point. So those are the 2 points I'm using. Let me just record there that I'm using this point as x1, y1, and this point here, this is x2, y2. Okay, so now let's go ahead and unpack this formula. Let's substitute in x1, x2, y1, and y2. So I have here that c is the square root of, let's see, what is x2? That is b cosine of c. x1 is just a. y2 is b sine of c. And y1 is just 0. All right, so I'm using the distance formula to get the length of this side here. All right, now let's see what we can simplify. This looks like a kind of a nightmare, but actually some parts of this I think are going to come out kind of nice. So if I square that first set of parentheses, I get b squared cosine squared of c minus 2ab cosine of c plus a squared. And I'll explain that in just a second. I want to go ahead and square this other thing first. So here I know that this is just, well, the subtraction by 0 doesn't really matter. This is just b sine c. The square of that is going to be b squared sine squared of c. Okay, one idea that I'm using here when I'm squaring this is I'm using the fact that if I square p minus q, that is the same thing as p squared minus 2pq plus q squared. If you were to actually write this out, p minus q times p minus q and distribute, this is exactly what you would get. Okay, and that's exactly what's going on here. All right, next step. At this point, you may notice something kind of nice going on here. You might notice that I have a term here, b squared cosine squared of c, and another term here, b squared sine squared of c. Let's try putting those together. So I'm going to put those together and factor out a b squared. And then leave this a squared here, and then minus 2ab cosine of c. So just pull that square root over a little bit. There we go. It's a nice multicolored square root sign. And we know that cosine squared of c plus sine squared of c is just 1. So that whole term there is b squared times 1 plus a squared minus 2ab cosine of c. And the last thing I'm going to do here is I'm going to square both sides, because it's traditional that when we write the rule that I'm about to get, I usually just leave the square root off and square both sides. And I get this, which may look familiar if you've ever taken a trigonometry course before, maybe even if you've taken a good geometry course. This rule here is called the law of cosines. And it tells me, let me zoom out here, it tells me if I'm given a triangle like this one up here, and I'm given the length of this side, the length of this side, and the measure of the angle between those two sides, I can always find the length of the opposite side. And this theorem here is stated in terms of A, B, and C, like I've got A here and B here, and then the C is over here, and C is the special angle whose measure I know. But that doesn't have to be the case. I could give you a triangle where maybe you're given angle A, and you know sides B and C, and you want to find the length of side A. You can still use the law of cosines. You just have to rename things. Okay. The main idea I want you to take away is not that the A goes here and the B goes here and the C goes here, but rather these are two sides of the triangle, the squares of the length of those sides. This is the angle between them. This is the product of those two sides. And this expression gives me the square of the length of the other side, the side opposite that angle. And we came up with that just by doing a little geometry problem here. I mean, I realized that I could have just said at the beginning of the video, here's the law of cosines, here's the formula, here's the proof. But I kind of wanted you to appreciate that this law, which is very famous and extremely useful in geometry, just comes out of considering a simple problem about triangle measurement and thinking about techniques that we might have from trigonometry for measuring where these points are. Because once we measure the locations of those points, A0 and B cosine C, B sine of C, that's this point here, once we have those locations, we can just use the distance formula to figure out the distance between them, and that's the length of the other side. Anyway, I hope you enjoyed that. I know that I did.